what we want to talk about here is all the different forms. We have these different, we have blackbody radiation, we have radiation from surfaces, we have wavelength dependent radiation. Let's just kind of sort out what all those things are and have definitions ready for them. So first, let's start off with blackbody spectral emissive power. I'm just going to abbreviate blackbody with BB. So BB spectral emissive power. Okay, so this is denoted EB lambda. This is the one we were just working with. So EB lambda has units of watts per micrometer meter squared. So this is, let's see, so this is a function of wavelength, function of wavelength. It is the maximum possible emitted power at a given wavelength. So actually what I want to do over here is just plot some of this stuff out as we're doing it. Okay, so here what we're going to plot is we're going to plot some emitted power, right, E lambda, and here we're going to plot wavelength on the x-axis. So our emitted power, right, if we were to try to plot blackbody spectral emissive power, this is what we're doing. It would look something like a blackbody curve. So it would look something like this. Right, it's just our blackbody curve despite my squiggly drawing. So that's our, let's just label this. This is E lambda. So that's our blackbody curve. All right, the next thing is going to be spectral emissive power. Right, we denote this with just E lambda. This again has units of watts per micron meter squared. What is this spectral emissive power? The only difference between this and EB is the fact that it's not a blackbody, right? So this is actually a real surface's emissive power. If we draw this out, you know, I could draw it out for any surface that you have, but it would be some real surface. So it's going to be never going to be greater than the blackbody. It's always going to be less. It could approach the blackbody. In some regions, it might be really close to a blackbody emitter. In some regions, it might be not at all close. So it might look something like, you know, just making something up. It could look like this, right? So this could be our real surface's emitting profile. We call this plain E lambda. So just make a note here that this is real surface. Okay, the third thing is emissive power. So emissive power, we just denote this with the symbol E. And so emissive power is going to be, now it's just watts per meter squared. Okay, so now we're no longer, for emissive power, we're no longer concerned with a single wavelength. This is the total power emitted, I guess in this case, from a real surface. So let's see, what does that mean? I have to actually integrate the entire function in order to get rid of the single wavelength. So this would look something like, what, let's integrate. So this would be all this area under this real curve here. So this here is going to be E. The formula for this is just, or generally, right, it's probably obvious, but it's just E is equal to the integral from 0 to infinity of E lambda d lambda. So just integrate that curve from wavelength of 0 up to infinity, and that gives you the full power emitted. All right, so the last thing then is blackbody emissive power. Okay, we denote that with E sub B. That also has units of watts per meter squared. This is going to be now the integration of our EB lambda over all wavelengths. So I'll pick a different color here. So this would look something like this this full area here is going to be EB. Okay, EB, the formula for that is again the integral. So EB is going to be the integral from 0 to infinity of what EB lambda. D lambda. More specifically, it's the integral of Planck's law, right, which is our expression for EB lambda. We would write that out as from lambda equals 0 to infinity. Planck's law is C1 over lambda to the fifth exponential of C2 over lambda times T minus 1 d lambda. Okay. There's actually a much more convenient way to write this. And that is something you're familiar with. It's sigma T to the fourth. Right? So we've gone this whole time, this whole semester, saying, let's just assume that we have some power for radiation, sigma T to the fourth. That's actually the result of doing Planck's law integral over all wavelengths. Okay. So anytime you're talking about the total Blackbody power, it's going to be sigma T to the fourth. By the way, let's just be clear. Sigma is 5.67 times 10 to the minus 8th. That is watts per meter squared Kelvin to the fourth. Right, that's the Stefan Boltzmann constant. Probably the easiest constant to remember in engineering. Must use pi equals 3, I guess. Okay, so that's all the definitions we kind of need. So any questions on this so far? Kind of straightforward to go through this. All right. Okay, so let's talk a little bit about, the fact that we have previously assumed that emitted radiation is just sigma T to the fourth, but now we're given this Planck's law where we can do the integral over, say, a region that's not the full 0 to infinity. We could do the integral over some other region, and maybe, why would we want to do that? Well, let's look at my E lambda curve up there. So my E lambda curve shows some features where in the low wavelength region, it's really close to a black body. So I could model my E lambda surface in that region as, say, a black body surface, but I need to be careful to break up the integral and say, yeah, in this region, it's a black body. I can compute the amount of energy in that region only, in those wavelength, specified wavelengths only. And then I can do something else outside of that region. So it's often done where we actually want to break up our integral into different pieces and treat those separately. And actually, this gets to something that we'll talk about later called gray bodies. Okay, so let's think a little bit about how to break this up. So let's say here our black body emissive power in a specific range or wavelength range. So we're going to write this as EB, since it's a black body, EB from, say, lambda 1 to lambda 2, or we could just say, for our example here, 0 to lambda 1. Right? And that's going to, again, have units of watts per meter squared. We're integrating, but it's only in this range from lambda equals 0 to lambda equals lambda 1. So if we do that, right, you can write out the integral again, Planck's law here, but we just are integrating from 0 to lambda 1 instead of 0 to infinity. What does that look like? Well, in the curve here, we might see, I'm just going to plot it out just to be clear. So you might have your black body curve. So I might say, okay, I'm going to look at this being my lambda 1. This over here is 0. I'm obviously just going to take the integral of this region here. So why is this useful? Well, again, you can break up surfaces, treat them separately, and then do analysis separately on each part of the surface. This is actually, the process of doing the integral of Planck's law integral is actually not that straightforward. Right? It's a kind of a difficult integral to do. So there's something called external fractional functions that have been tabulated for you. So external fractional function. An external fractional function is a representation or a tabulation of this integral, but on a fractional basis. So what does that mean? Well, I've got over here my integral from 0 to lambda 1. If I take the integral as well from 0 to infinity and divide, right, so this integral EB from 0 to lambda 1 divided by the full integral EB 0 to infinity, right? That gives me this fraction of power that's emitted in that region. Right? My external fractional function gives me now a fractional value that for a given wavelength and wavelength band and for a particular temperature is going to tell me the fraction of radiation emitted in that band. All right. So just to write that out, to give you kind of a full definition of it, it looks something like this. We'd say my fractional function from, say, 0 to lambda 1 is going to be the integral from 0 to, well, let's save the integral for a second. Let me just write out Planck's law first. So C1 over, let's see, lambda to the 5th times exponential of C2 over lambda t minus 1. Okay, so what I want to do is I want to divide that Planck's law by sigma t to the 4th. If I do that, I end up with here in the denominator sigma t to the 4th, but see there's also a t in the denominator over here. So we end up with writing this out as follows: sigma t. So sigma times lambda times t to the 5th. All right, let me make sure you got this. Okay, so then here d lambda t. Okay, so this is our integral. So I kind of pictured this. So we'll write this out and I'll explain what happened. Okay, so we have Planck's law. We divided by our Blackbody emissive power. And what we want to do is take our integral over some variable. Okay, but it actually turns out that because lambda and t are not fully independent of each other, we'll just take those together. And it makes it, you're taking as one variable of the integral. Okay, so we go from 0 to lambda t, the product of those two things, and we evaluate this integral, and this gives us our fractional function. Okay, kind of got to that backwards. Any questions on that? Okay, so for practical purposes, what you need to know is this is a definition, but how do you actually use it? How you're actually going to use it is going to a table. Let's look at ease for a second. So in ease, there's a function called Blackbody. You can get to that either by typing it in, or you can look at the, ease library routines. So the first one listed here, you can see is Blackbody. So if you look at that function, Blackbody is looking for you to give it a temperature. Looking for you to give it lambda 1 and lambda 2. So you're going to give it a range of lambdas that you care about, where you want to evaluate your fractional function. You give it a temperature. What it's going to return for you is the fractional function between those two wavelengths. And so I'm going to say F is equal to Blackbody. So why don't we take, for example, I don't know, the temperature of the sun, so 5,800 degrees Kelvin. And let's say I want to look at the visible range, which was 0.38 micron. It's a little bigger for you. Okay, so 0.38 to 0.78 micron. By the way, that's how you write micron units. It's micrometers, micron used. So if we do this, we should get back the fraction of light that is emitted by the sun in the visible region. And if we do that, we see, yeah, roughly half, a little less than half of the light emitted from the sun is in that visible region. So you can do this for two different wavelengths. You could do it from, right, so let's say we wanted to know how much is in the UV region. Let's say micron here, and then let's get rid of. So these are all the high power rays that could potentially be damaging to humans. So something like 10%, right? So 10% of all the light that's emitted from the sun can kill you. Right? Fortunately, we have things like the ozone layer to stop that from happening. But if you're out in space, this becomes a really big issue. 10% of the light hitting you is potentially problematic. Okay, so that's the Blackbody function. Yeah, one last thing here to look at. So if you actually plot it out, so this, so if we actually plot out this function, it's actually just one curve. So remember what we're doing here is we're looking at the product of wavelength and the temperature and using that to compute the fraction of light. So give me a temperature and then the corresponding wavelength region, and you can calculate the fractional function based on the product of the temperature in absolute units in the wavelength. Right? So here's a plot showing, all right, if that product is pretty low, then the fractional function is going to be close to 0. If the product is really large, it's going to go to 1. And you're always going to be bounded between that 0 and 1 region. So you could use these for this, or you could actually just go to this table, you manually calculate the product of two things and say, you come up with your product of 5,000, you come out and you pick out, okay, so this is my fractional function in that region. If you do use a table like this, remember this is the fractional function between 0 and the product. So if you want to look at the difference between two wavelengths, you'd have to take, you have to evaluate this twice and then take the difference of those two.